In the second half of chapter 14, we learn how to accumulate functions over a surface instead of a flat surface like dx dy. So we talked about parametric surfaces because we use this to integrate our functions if we have to change it to parametric systems. We talked about surface integrals, therefore, and we talked about divergence and Stokes theorem, which kind of connects our double integrals to our triple integrals, and likewise our path integrals to our surface integrals. So I'll start by reviewing how to write different things into parametric mode in case we need them. These are 3 examples similar to the ones that we did in the homework. Basically, what you have to do is define this in terms of 2 variables instead of 3 variables. So for example, with a plane, you could let z equal 7 minus 2x plus 3y all over 5. And then you could use x and y as your 2 parametric variables instead. So r of xy would equal x, y, and then z in terms of x and y, 7 minus 2x plus 3y all over 5. Now, if you have something like example 2, you do want to think of the conic sections that we have done throughout the course of the unit. So this one, something squared plus something squared, looks very similar to a sphere, and that's what we're actually going to use in it. It would be a sphere of radius 1 because it's equal to 1, and basically what I want to do is set this up to look more like our spherical format. So this would be 3x quantity squared plus 4y quantity squared plus 2z quantity squared equals 1. And then you can think of 3x, 4y, and 2z as my x, y, and z components in spherical coordinates. Now, rho is equal to 1. So then 3x would normally equal rho sine phi cosine theta. So in this case, it's going to be 1 sine phi cosine theta. 4y would equal 1 sine phi sine theta. And 2z would equal 1 cosine phi. So my parametric surface for this is going to be r theta phi. X is going to be 1/3 sine phi cosine theta. Y is going to be 1/4 sine phi sine theta. And z is going to equal 1/2 cosine phi. Now, to make sure that it expands around this entire surface just once, I need to give some bounds to theta and phi. So theta, using normal spherical coordinates, is going to be between 0 and 2 pi. And phi is going to be between 0 and pi. The last one recalls our rotations back in chapter 10 as well. So I'm going to graph the line y equals 4 over x, assuming it's on the xy plane. Rotating about the y-axis is going to generate circles in this direction. So the circles are parallel to the xz plane. So we're going to write x squared plus z squared to represent the equation of our circles for various values here. Now, the radius is defined by either the z-coordinate or the x-coordinate. And I have to figure out which one I can solve for. So since there's no z equations in my variable equation here, I'm going to have to solve for x. So x would equal log of y base 4. And so my radius is log of y base 4. So same thing, I'm going to change this to our trig identity. So if I think of cosine squared plus sine squared equals 1, this would mean log of y base 4 cosine theta, or sine theta squared, plus log of y base 4 sine theta squared would equal log y base 4 squared. So matching coefficients then, I'm going to let log y base 4 cosine theta equal my x, log y base 4 sine theta equal to z, and then that'll be my last component. So my parameters for this parametric surface would be theta and y. X component, like I said, is log y base 4 cosine theta. Y is the variable I didn't change, so I'm going to leave that as a y. And then my z component is log y base 4 sine theta. And now for my bounds. So x was originally between -1 and 3, y equals 4 to the x, so that means that y has to be between 4 to the negative first and 4 to the third. Theta is my other parameter. Since it's coming from cosine theta minus sine theta, cosine theta is going to be between 0 and 2 pi. Let's start doing some of the other applications we had with parametric surfaces. So we talked about tangent planes and surface area. Let's start with the tangent planes. Now, to write a tangent plane, we need a normal vector. And the normal vector was equal to r sub u cross r sub v. And that's because RU and RV are both tangent to the surface, and so if I cross two tangents, I will get the vector normal to the surface. So R sub U equals 3, 1 over U, and 0. At this point here, this would be when U equals 1 and V equals 1, and to double check, that would make natural log of UV equal to 0, so that's good. So substituting in U equals 1, I'm going to get R sub U to equal 3, 1, 0. Similarly, R sub V would equal 0, 1 over V, and 2. So the vector at that particular point would be 0, 1, and 2. The cross product, R sub U cross R sub V, would equal 2, negative 6, and 3. And again, that is my normal vector. So the plane would be 2 times x minus 3 minus 6 times y minus 0 plus 3 times z minus 2 equals 1. Now, surface area component. So, RU cross RV's magnitude would represent the area of a parallelogram defined by RU and RV. So if I add up all these parallelograms, double integral of RU cross RV, I will generate the surface area for this region between 1 and 3 and 2 and 5. So U's going from 1 to 3, V's going from 2 to 5. I'm going to take my RU and RV and cross them from above. So RU cross RV is going to be 2 over U, and then negative 6, and then 3 over V. And then this is dV du. So the magnitude of that, from 2 to 5, would be the square root of 4 over U squared, plus 36, plus 9 over V squared, dV du. And both of these, or the surface area one, we will be using a piece in our surface integrals. So next, let's do some surface integrals. What I tried to do here was I tried to use integrands that almost looked like each other and surface, at least for the first two examples, that were exactly the same. So you see the difference between a multivariable function and a vector field. So let's do these one at a time. Let's start with the multivariable function. You can recognize it's a multivariable function because there's no vector symbols anywhere. All I have is a function times ds. So what we're going to do is we're basically going to solve for z here. So z equals 10 minus 2x minus 3y over 5. And that's what I'm going to substitute in for the z component. My ds is my surface area component. So that is the square root of 1 plus z sub x squared plus z sub y squared. And so putting all of this in, it's now going to become x squared times z, 10 minus 2x minus 3y all over 5, plus y. So that's my integrand. My ds is 1 plus negative 2/5 squared plus negative 3/5 squared. And what I need to do is I need to integrate this over the projection onto the xy plane. So this is dy dx. So what I have here is I have a plane projected onto the xy plane would be this triangle. So that triangle goes from 0 to 10 minus 2x over 3, and x goes from 0 to 5. So that would be a multivariable function. Now let's do the vector field. So for the vector field, now what I'm going to do with my z equation, 10 minus 2x minus 3y over 5, is substitute it into my vector. And then I need to dot this with my unit normal vector. So I actually will want to do this two ways. Let's start by just doing it the straightforward way. Alright, so n is going to be generated from the surface. And my surface is 2x plus 3y plus 5z equals 10. And what I'm going to do is I'm going to take the gradient. So del of s, let's say, even though that's not correct notation, would be 2, 3, 5. And then normalized, since it's a unit normal. So how about I just call this n then? Magnitude of 4 plus 9 plus 25. And then ds is my square root of 1 plus z sub x squared plus z sub y squared. So if I solve for z here, I'm going to get that 10 minus 2x minus 3y over 5. And so this would be square root of 1 plus negative 2/5 squared plus negative 3/5 squared. So I'm just going to build this integral one piece at a time. So my f is now x squared z 10 minus 2x minus 3y all over 5, comma, my y, dot my n, 2, 3, 5, over square root of 4 plus 9 plus 25, times my ds component, 1 plus negative 2/5 squared plus negative 3/5 squared. Again, we'll do dy dx. So y would go from 0 to 10 minus 2x over 3. X would go from 0 to 5. Now, notice in this particular example what I did, the terms here, this factor and this factor do not cancel out. But you would get the same value as what I'm going to do next. So I'm going to show you the way that we've been doing it typically in class. So what we did in class, this is option 1, this is option 2. In class, what we did was we redefined the surface so that the coefficient of z was equal to 1. So if I do that here, my n is going to be derived from 2x over 5 plus 3y over 5 plus z equals 2. So all I did was I took this equation here and I rewrote it. So if I do that and I set up my integral, it would still be from 0 to 5, still be from 0 to 10 minus 2x over 3, x squared, 10 minus 2x minus 3y over 5, comma y. That still stays the same. Dot, this time my normal vector is going to be 2/5, 3/5, 1, all over the magnitude of 2/5 squared plus 3/5 squared plus 1 times my ds component, which is still the same as this ds component, 1 plus 2/5 squared plus 3/5 squared. And it was dy dx. So these two cancel. But again, they are equivalent because in this particular term, if I were to factor a 25 out of the radical, I would end up with a 5, 2, 3, 5, all over 2/5 squared plus 3/5 squared plus 1. And then notice my top becomes 2/5 3/5, and 1, which is similar to what I have in red. So they are equivalent answers. One is just using the normalized unit normal vector, and then the other one is not normalizing it initially, but normalizing it afterwards. The last one I have here is just something to do a little bit differently. And again, this one is a multivariable function because it's y times ds. There's no vector symbols anywhere. And I've already got z solved for. So for this one, y is good. ds is the square root of 1 plus z sub x squared. So that's x over square root of x squared plus y squared, quantity squared, plus y over the square root of x squared plus y squared, quantity squared, dy dx. Now graphing this is a cone, and I'm interested in the surface of the cone between z equals 1 and z equals 3. So if I project that onto the xy plane, I generate two circles, one circle of radius 1, the other one of radius 3, and I'm interested in the surface area between those two. So I need to project it onto those two circles. So this would be an ideal time to use polar, because in polar, I would set up the interval from 0 to 2 pi. R would go from 1 to 3. Y would be r sine theta. The cone is really nice because what this reduces to is x squared plus y squared over x squared plus y squared. So actually all that reduces to square root of 2. And then my r d theta for my polar unit for dy dx. Alright, we also learned two special theorems, the Divergence Theorem and Stokes Theorem. Divergence Theorem is when you integrate a surface over a surface, and the surface happens to be a solid that you're working with. And what that means for the Divergence Theorem is you can actually integrate it as a volume integral instead of a double integral. So graphing this over here, I have x plus y squared equals 9, or x equals 9 minus y squared. So that would look something like this, only in the first octant, and then z is between 0 and 4. So I'm looking at that solid there. So that is your clue that you want to use divergence theorem for this. So to review divergence, div f is del dot f. So that's d dx of the first component, which is 1, plus d dy of the second component, which is 3y squared, plus d dz of the third component, which is negative 1. So that reduces to 3y squared. So I'm going to rewrite this as a triple integral of div f dv. And so div f is 3y squared. Another clue to use divergence theorem is if it is over a solid, take the div. If the div is a lot easier to work with, then use the divergence theorem. If the div ends up being really complicated, you might be easier just doing surface integrals instead. So 3y squared is the div, which is definitely a lot easier. Let's go ahead and do dz, dy, or dx, dy for this one. So z goes from 0 to 4. I wanted to do x because x goes from 0 to 9 minus y squared. So that just kind of worked out nicely. And then y goes from 0 to 3. Oh, z goes from 0 to 4. Okay, so that is divergence theorem. Now Stokes theorem connected our line integrals to a variation on our surface integrals. And the way you recognize using Stokes is if you're integrating over a path, and the path is generated from the intersection of a surface and a plane. So let me kind of show you here. Here I have the intersection of a upside down paraboloid, something like this, and the plane z equals 2. So I generate this c, and of course it's always oriented counterclockwise. And then notice c is a planar surface, so that's a nice one to represent parametrically. And what we can do then is Stokes says that the integral of c f dot dr is equal to the double integral of the curl of f dot n integrated over the original surface that defines C. So this is my S surface, this is my C. Now, N has to be oriented outward. So if C is going in the counterclockwise direction, N is going this way. And so we are going to have our dz component in N equal a positive value as a result. Okay, so let's go through each of these pieces one at a time. Curl of F is I, J, K, ddx, ddy, ddz of x squared, z squared, and negative xyz. So the curl for this is negative xz minus 2z, negative of the component negative yz minus 0, and then my last component is 0 minus 0. So it looks like my curl is negative xz minus 2z and yz. I'm going to double check that. So negative yz x squared, and then 0, oh, actually this one's just 0. Yeah, so negative xz minus 2z, and then negative yz, but negative, and then the other way 0 and 0 and 0. Okay, so there's my curl F. My N is defined from the surface. So again, I need my z component to be positive, so we'll make that x squared plus y squared plus z equals 8. We'll take the gradient from my n vector. So now n is actually equal to 2x, 2y, and 1. And over its magnitude. So I will actually just spell this one out. So this will be 4x squared plus 4y squared plus 1. So I will set up a double integral for curl f dot n ds. Curl of f is negative xz minus 2z yz 0. Should be a 0 up here. Dot my n component, 2x 2y 1 divided by its magnitude, 4x squared plus 4y squared plus 1. And then my ds component, which is the square root of 1 plus z sub x squared, which is negative 2x squared, plus z sub y squared, negative 2y squared. And you can see these two cancel each other out as well. Okay, so let's say d, doesn't really matter. So let's say dy dx. Alright, so I need to find the equation of the projection, and the projection would be the intersection between the paraboloid and z equals 2. So intersecting the paraboloid and z equals 2, I'm going to get x squared plus y squared equals 6. Let's make sure. 8 minus x squared minus y squared equals 2. So x squared plus y squared equals 6. So we will make y go from negative square root of 6 minus x squared to the positive square root of 6 minus x squared, and x to go from negative root 3 to root 3. Now, I'm actually not quite done, because notice in here I have a couple of z components. So I do need to replace that to have my complete final answer. So my final answer for this is going to be negative root 3 to root 3, negative square root of 6 minus x squared to positive square root of 6 minus x squared. And let's factor out the z. So this will be negative z, which is 8 minus x squared minus y squared. I have an x plus 2 left over, comma yz, 8 minus x squared minus y squared, comma 0, dot 2x, 2y, 1, dy dx. And that would be the surface integral of the equivalent line integral. Good luck studying for the test, everyone. Please stop by the classroom if you have any questions.